Okay, sorry, I'm back. The total frequency shift between these two is tiny for Brillouin scattering compared to Raman scattering. Right? This frequency is also known as the Stokes shift. There's also, in addition to the frequency shift, there's an issue of how much frequency bandwidth is available. In Brillouin scattering, it's again tiny. Right? This is small compared to the other one. This is tiny. Right? There's not much bandwidth in this process, so but there's huge amounts of bandwidth in the Raman scattering, and that's why stimulated Raman scattering is used to make Raman fiber amplifiers. And therefore we have Raman fiber amplifiers. Sorry, I'm rattled when people are talking in my classroom and they're not students in the class. All right, so think about it. Look at this energy diagram. All right, it's a lot like the EDFA, right? Except in the EDFA, we pumped it up. There was a bunch of little levels that it could trickle down. We had a population inversion. Here we also can have a population inversion. We pump up to here, right? It sits in pump photon of this color, cranks it up to there, and now I've got gain for this color. Right? So I can make an amplifier out of this too. The only difference is in this one, when I come down into one of these vibrational modes and I make the crystal move around a little. Okay. All right. Now, we can talk as much as you want about nonlinear optics, but one of the things I want to connect back to is something similar to what we did with the birefringence. And that's the so-called electro-optic effect. Sorry, after any scans that got a little fuzzy. We tried to take it right from the original source. But a lot of people have heard of this electro-optic effect, right? So let's call it electro-optics. It doesn't sound right. In electro-optics, it's non-linear. In fact, it's a Chi-2 process, which means there's two waves involved, two different frequencies. So electro-optics is nonlinear optics. It's a nonlinear processor. It refers to nonlinear optics. But one field is essentially at DC. At DC for optical people means maybe 10 gigahertz. Okay, hard to think of 10 gigahertz as DC, but compared to optical frequencies, it is. Okay, so in an electro-optic device, I have one optical signal coming in, and then I have this so-called DC, which is my information, and then I have optical coming out. But the mixing here of the two waves, one is an optical wave, and the other is the so-called DC, and then something comes out that's been modified. An electro-optic device does exactly what the birefringence does. It slows down one axis, one polarization with respect to the other, but it does it in a way that it's this voltage that I applied determines the difference in speeds between those two axes. So it's like birefringence, but birefringence, I don't need any DC field applied, all right? With a quarter wave plate, It's just that. So it's not nonlinear, right? With electro-optic devices, it is nonlinear. Okay. Here's an example. Our good old friend lithium niobate is also very good electro-optic material. Input one signal, this could be one polarization going into it, and then this is a splitter, right? Rather than being done in fiber, this is done typically in integrated optics, where you make your little waveguide sitting on top of some type of substrate. You can deposit some electrodes here, right? And then apply a voltage, plus minus voltage V1 here across these electrodes, produces an electric field E1. That's my so-called DC field, although this could be, you know, 10 gigahertz. Right? Then it's going to control the amount of phase shift between one polarization and the other. Likewise, I do that down here in this path of what's basically an interferometer. Right? I'm splitting a signal. It goes through one phase shift, the other signal goes through another phase shift, and then they recombine here. They're being added back together. Right? Likewise, across these electrodes, I produce this other electric field E2 by applying a voltage plus or minus V2 here. This is an electro-optic modulator. Okay, what can I do with it? Well, clearly, if I can make it so that the phase shift the upper arm sees is different than the phase shift the bottom arm sees, then I can make them add up here at the output, either in phase or out of phase. So I can create dark spots or bright spots. The transmission of this device, if you want to Wikipedia transmission coefficients, you'll see that what I'm really talking about is the magnitude square of that. But we can just think of it as how much gets transmitted. Transmission through the device is going like cosine squared of the phase difference between the two. Sorry about the fancy notation, but J could be 1 or 2. This is just a proportionality constant. It's in green, so it's kind of an aside. But no, you can handle this. The phase that I go through is proportional to the voltage that I put across it. Okay? So I have a phase phi sub 1 controlled by V1, phi sub 2 controlled by V2. Right? So I can control these two phase shifts. And so what can I make out of that? For example, I could make an on-off modulator as I was hinting at. If we make one of these voltages equal to the minus of the other, then they'll add up here. Don't worry about the factors of 2. I'm also going to add a little bias voltage on this one. Show you why in a minute, but that would show up like this. So I have something like cosine squared of, I've forced one to be the opposite voltage of the other, then it's just that. So I just have to plot this transmission as a function of one voltage. Ignore this little line here. I was going to give that a name, but I decided not to. It's a raised cosine. Cosine squared is always positive. This little VB voltage controls how I can move this. I can bias this transmission curve so that I can move this to any operating point. Why? Because I might want to make it nice and linear. So instead of having this raised cosine, which goes to 0 down here. If VB was 0, cosine of the, well, anyway, wherever it is, I can move that point. I can move that 0 point. I can move it to where the transmission is more like this part of this curve, rather than having, you know, some nonlinear portion here at 0 volts. I can move it to where it's making more of a transition from off state to the on state. Here, very little is getting through the device, and here, most of it's getting through. So I can turn things on and off, right? That's an on-off modulator. Okay. And being able to bias it is kind of nice because, you know, maybe I don't want to have to apply a lot of voltage to it, right? I want V1 to be small. I can add or subtract some VB to essentially move this curve back and forth so I can have any operating point I want. As per our discussion, you know, maybe I want to make an amplifier, a linear modulator out of this, all right? If I am just operating over this range, everything's linear, right? I could make it go up and down proportional to that voltage. Or if I want to drive it this hard, I can make it go all the way off or all the way on, okay? So, it's a useful device. Can I make a phase modulator out of that? We said, well, we have these coherent schemes that really would like to be where I put the information instead of on and off, put the information into what's the phase, right? If you want to do the math, you can set that voltage equal to that voltage rather than the minus, and then the phase difference goes to 0. Cosine of 0 is 1. So now I'm always at peak power transmission. And if we go through it, then the transmission becomes just phase shift. So, well, that makes sense, right? The whole point of this electro-optic device was to impose a phase shift on it, one polarization versus the other. Okay, so what can I do with that? Well, for example, and all this is in Agarwal and probably Wikipedia. If you want to know more about it, for example, if you wanted to do a term paper on that, pick a term paper topic on something that you want to learn more about is always a good idea, right? Phase shift keying, so-called Q phase shift keying. I don't like it. I'd rather call that 4 PSK. Like it or not, a lot of people call it quadster phase shift keying. Okay, gotta have more names for everything. Here's how you can build one of those. Have the device we were just talking about, an electro-optic modulator, make both voltages the same. Now that box is just a phase shifter, right? Bring in another one, right? And again, split the signal, go through this phase shift box, and then add the two back together. Aha. Then, what's the easiest way to see that? This voltage gets the I data, maybe the in-phase data, and then this one gets the quadrature data, Q data. We set this voltage, this is all still in an electro-optic crystal. This voltage can be set to put a 90-degree phase shift between the top and the bottom, so that the top one works like cosine and the bottom path is working like sine. And then that's why this one would be the I data modulating the cosine, and this one would be the Q data modulating the sine. So I set things up so that there's a 90-degree phase shift between the upper and the bottom, this upper and bottom path. Okay? So for so-called QPSK, which is 4PSK, I've just got these 4 dots here. Then the phase shifts I need over here or over here would just be 0 or pi. 0 or pi. I can also think of 0 or pi as a plus or minus 1. Okay. But let's see. Could I then make a QPSK modulator out of this? That might make a good homework question. We'll see if it's on that homework 3. But what do you think? I can make this phase shift anything I want. I can make this phase shift anything I want. But if I've already set these two to be sine and cosine, then well, what about making this V1 and minus V1? Then that little box there becomes an on-off modulator. Okay. Can I do 4 level with just on and off? Yeah, those are probably a little tricky for homework, so take a look at the homework and you'll see much simpler questions than the ones I'm teasing you with, just to get you to think. All right, I think that should be enough on that one. I thank you for all your patience, and I think you'll enjoy homework 3 once I am there to do the solutions. Remember, you're splashing around. It's a good way to learn, and I look forward to seeing you on Tuesday when we can do homework 3 solutions. Thanks. Good night.